is. Okay. Okay, we're going now. Okay, so today we are going to explore sine, cosine, and their inverses, which are called arc sine and arc cosine. We're also going to touch on tangent just a little bit, but our main focus is going to be on sine and cosine. Our standard is 12.2.1. Not that that makes a huge difference for you, but so our objective for today is by the end of the lesson, we should be able to understand the basic concepts of sine and cosine and apply them to solve simple problems. So our goals are going to be understand the concepts and the basic meanings of these things, and then building off of that, we're going to break down our problem solving skills and try to apply this to a few examples that we haven't really seen before. So just a little open-ended question. What are sine and cosine? Does anybody know? Don't look at the answer. That's cheating.
Are you wanting like a literal answer or like what do you? Oh, there you go.
Here we go, right here. Yeah. So
Triangles.
yeah, my iPad sync isn't working, so I can't draw it out. But it's a ratio of the sides of triangles. So if we looked at the different, let's see if I can draw something here. If we looked at a triangle and we said, here is a triangle. It's going to be very difficult because it's drawing on a computer keyboard. If we call this theta, our sine function, remember our little acronym is so. So that means it's going to be opposite over hypotenuse. So to break that down a little bit, the opposite angle is straight across from the angle here, and the hypotenuse is the longest side in a right triangle. So that'd be this one. And if we did cosine, that would be containing the adjacent angle. So if we remember, cosine is adjacent over hypotenuse, so like this. And if we look at theta here, the adjacent side is going to be this one, because this is theta and it's the one connected to the angle, right? And then if we did the same thing for tangent, we would say TOA, because so, ka, TOA, right? And then if we drew a triangle, it would be the same involving sine and cosine. So if we did this theta here, our opposite angle, again, would be here, and our adjacent would be here. So let's apply this to an actual example. Sorry, my technology is not being there. Let's apply this to an actual example. And let's look here. And my note here is that, remember that we only use this in right triangles. If we had a triangle that didn't have a right angle, we would have to use something called the law of sines or the law of cosines. We're not going to talk about that today. If we look here, we have a triangle. It is a 3, 4, 5. We know that this triangle works. We could prove that with the Pythagorean theorem, but we're not going to do that because our focus is not on that. If we want to find the sine of theta, how should we go about that? Well, remember, our acronym is so, ka, toa. So sine is opposite of our hypotenuse, right? So if we have theta here, what is our opposite side going to be?
3.
3, that's correct. So we have 3. And our hypotenuse, what would that be? 5, correct. And if we look here, that's right. So this is pretty simple, and it's just 3/5. And then if we were to do the cosine, we're going to follow the same process, right? But this time we want adjacent over hypotenuse. So if we take this angle, what is the adjacent side to that angle? 4, that's right. And if you're thinking 5 looks like it's adjacent also, yeah, you are 100% correct. But 5 is the hypotenuse, and we want to differentiate the hypotenuse from the other side. So when we ask for the adjacent angle or the opposite angle, we want to talk about the sides that are not the hypotenuse or the angles that aren't opposite from the hypotenuse. So cosine, like you said, is going to be 4, and our hypotenuse is the same from above. So it's just going to be 4/5. And then if we talk about tangent, we're going to have opposite over adjacent. And as we said earlier, our opposite is 3, right? Because we did that on the sine function. And our adjacent is 4. So for that, we're just going to have 3/4. So let's try another example. This time we are looking at the angle B. We're going to call this theta right here. And if we're going to try to find the sine of this angle, where should we start?
Find the opposite.
Opposite, right? Opposite over hypotenuse for sine. And this is my opposite angle, right? Or side?
No.
No, that's right. Good catch. This is the opposite side. So the opposite is going to be 5. And our hypotenuse, what's that going to be?
13.
13.
Right. Okay, so based on what we've learned, opposite over hypotenuse, we have sine of b equals 5/13. Now, if we want to find cosine, we need to find the adjacent side, right? What looks to be the adjacent side of our angle?
12.
12, right. So we have 12 over 13. And then finally, we have tangent, which is opposite over adjacent. And I think that this should be fairly easy. Opposite is what again?
5.
5. Good. We're going to have 5 over, and our adjacent side is
12.
12. Good. So thinking about this, we can see that it's given sine of an unknown angle. We can pretty easily find a ratio of side lengths, which are what sine and cosine are. But it gets a little more complex when we think about trying to find that angle. So we can do the same process in reverse in order to find the value of our given angle. And within this, we're going to have two triangles that are always going to work and that are always the same, the side lengths and the angles. And these are special triangles within trig. We're going to have this 1, 2 square root of 3 triangle. And across from our 1, we're going to have 30 degrees. Across from square root of 3, we're going to have 60 degrees. And across from 2, we're going to have 90 degrees. This triangle is always going to show up within trig. And it's important to remember the values of the angles because it'll help us break down some more complex problems. And as we can see, our shortest side is across from our shortest angle, which is 30 and 1. Our second shortest side is our second biggest angle, which is square root of 3 and 60. And then our longest side, our hypotenuse, is across from our largest angle. We also have a similar triangle here, which is a square root of 2, square root of 2, 2 triangle. Or if we think about it, we can also do a 1, 1 square root of 2 triangle. These are the same exact thing. They're both going to have 45, 45, 90. And just to show that they are the same thing, we can take each side on this triangle here and divide it by the square root of 2. So if we take our 2 and our square root of 2, let's try to prove that. So 2 divided by square root of 2. Now I'm just going to do a little bit of algebra. I'm going to multiply by 1 in a fancy way. And square root of 2 times square root of 2 equals 2. So that'll be in the denominator. And this is 2 square root of 2. So this cancels out. And we see that square root of 2 is our answer, which we see on this triangle. And then we can do the same thing. Square root of 2 divided by 2 equals 1. And that's how these two sides are the same as the previous one. So it's just important to recognize these triangles whenever we run into them because it'll make our lives a lot easier. So let's try to apply this concept to this example. If we're given the sine of sine of theta equals 1/2, and we want to find theta, which is our angle, and let's call, or never mind. Let's say we want to find theta, and sine theta equals 1/2. How are we going to start this? So remember, sine is opposite over hypotenuse. So what we're trying to figure out is which angle is opposite of our length 1. Can anyone tell me what that is? Sorry, I forgot to move the computer.
30 degrees?
What'd you say?
30 degrees?
30 degrees, that's right. That's opposite. And if we want to find the hypotenuse, we can obviously see that that's 2. So the answer to this is going to be 30 degrees because we can see that if sine of theta equals opposite over hypotenuse, like we said here, and that equals 1/2, our opposite is 1 and our hypotenuse is 2. So we can do the same thing with cosine. Let's call this cosine theta. And this is going to turn into adjacent over hypotenuse. So if we want to find what angle is adjacent to 1, because we have 1 here, right? What angle would be adjacent to 1?
Square root of 3.
Well,
Oh, angle?
yeah, angle.
Oh, 90 degrees?
Okay, you are sort of right. This is 100% adjacent to 1. But where we run into a problem is if we use this angle, our opposite and our hypotenuse would be the same thing. So in this case, we want to use our adjacent angle to be 60 degrees. And that is going to be our answer for cosine of 1/2 because our adjacent is 1, our hypotenuse is 2, and we can see how that works out. So let's try the same thing for this example. If we have, like it says, sine of theta equals square root of 3 over 2, how are we going to start this problem? Any ideas?
Identifying which one's opposite of
Right.
square root of 3.
Right. The sine is opposite over hypotenuse. And you said square root of 3.
Mhm.
So which angle is the opposite of square root of 3?
60 degrees.
60 degrees, that's right. So our answer to that question is 60 degrees. And then we can apply the same concepts to cosine of theta. And cosine of theta is what? It's what over hypotenuse?
Adjacent.
Adjacent.
Right, so if we're looking at square root of 3 again, which angle is adjacent to square root of 3?
30 degrees.
30 degrees, that's right. And like we mentioned earlier, 90 degrees is also adjacent, but we don't want to use the right angle. So cosine of theta, when it equals square root of 3 over 2, is going to be 30 degrees. Good. Now, this is going to be the same exact process, but this time we have a different triangle. This is our second of our 2 special triangles. And if we say sine of theta equals square root of 2 over 2, we need to find the opposite, like we said, over the hypotenuse. So which angle has square root of 2 as its opposite?
45.
45. Okay, are we going to use this one or are we going to use this one? It's a trick question. It doesn't matter. It'll give us the same exact answer. So if we say that this is opposite of square root of 2 or this is opposite of square root of 2, it's going to give us out the same thing. And our hypotenuse is obviously 2. And we can see that the 2 is going to be there and square root of 2. So like you said, it's going to be 45 degrees. If it's cosine theta equals square root of 2 over 2, what do we think about that?
Still 45.
Still 45, that's right, because we need adjacent over hypotenuse, and we can see that adjacent to this side here is 45 degrees, or if we were to use this side, this 45 degrees would also be adjacent. So in the case of our 45, 45, 90 triangle, or 1, 1 square root of 2, or square root of 2, square root of 2, 2, our sine and our cosine are actually going to be equal to each other. I want to show you something here. Nope. Nope. Here we go. Here, if this is the graph of sine, which is one of the functions we are dealing with, and we can see that when sine equals 1, our x value is pi over 2. So where does this pi over 2 come from? Well, if we go back to here, we have a fun tool within math called the unit circle. And the unit circle is measured in radians, which is another way to measure angles. If we think about degrees in radians, they're just two different ways to measure an angle. It's similar to like centimeters versus inches, and then we have radians versus degrees. So don't be confused as to what a radian is. It's just a way to measure an angle within a circle. And if we look, we can see that according to our unit circle, pi over 2 is the same as 90 degrees. Pi is the same as 180 degrees. 3 pi over 2 is the same as 270 degrees. And then 0 is going to be the same as 2 pi, because if we go around this unit circle, we can see that we're adding half pi each time. And if we add 1/2 pi to 3 pi over 2, that'll get us to 2 pi. So in order to prove this, I want to do an example of converting from radians to degrees. So like we said up here, we can see that pi and 180 are two equivalent things. So the best way to convert from radians to degrees or degrees to radians is to set up a simple proportion. And since we know that pi is equal to 180 degrees, we can use that in our proportion. And let's say we want to prove that let's say we want to prove that 90 degrees is equal to pi over 2, like the unit circle tells us. Well, according to our proportion, pi is equal to 180, and if we want to find what 90 degrees is equal to, we're going to put 90 degrees in the denominator, or the bottom of the fraction, because we want our degree values to be in the same spot, and then we want our radian values to be in the same spot. And if we set up a proportion here, we'll just put a variable x here. Now, based on algebra, we can just cross multiply, and we can say 90 times pi is equal to 180 times x. Now, simply, all we have to do is divide by 180 because we want to isolate our x value. And now we can say x equals 90 pi over 180. Does anyone know what 90 over 180 is equal to?
A half.
1/2, that's right. So x equals 1/2 times pi, or we can write it as pi over 2. And if we go back up to the unit circle, we can see that 90 degrees is in fact equal to pi over 2. So we did our steps correctly. And if we look at our answer, we can see that that is correct. Now, if we move to another example, how do you think we should start this? If we want to figure out what pi over 2 is equal to in degrees. I know we just did that, but this is just going to prove that we were right. So does anyone have any idea of how to start this process? Well, we're going to use this step 1 right here, similar to what we did in the above example right here. We're going to set up a proportion, which is written here for you. And then we're just going to cross multiply, because based on our law of proportions, that is something that we can do. And now we have pi times x, because multiply this together, equals 180 times pi over 2. We can rewrite this as pi x equals 180 pi over 2. And 180 divided by 2 is 90, right? So if we write pi x equals 90 pi, it looks like we're on the right track to get 90 degrees, right? So now we can just divide by pi, and we have x equals 90. And if we go back up to the unit circle, we can see that, like we said earlier, pi over 2 does equal 90. And if we go back to our graph of sine, we can see that this pi over 2 is also going to be equal to 90. So if you ever see that sine is equal to 1, you can say that the angle is 90 degrees, or you can say that it's pi over 2. They are two equivalent things. And we can also, based on our triangles, we ever have a right triangle, we can, instead of writing this as 90 degrees, we can write pi over 2 in this angle, and it means the same thing. So if we're going to do this process again, does anyone have any idea on how to start that?
You go to the unit circle and you find the
Well,
radius.
we could do it that way, but that's if we look up on this example and this example, the first thing that we did was set up this proportion right here, right? So if we're doing a similar example, what we're going to want to do is set up a proportion again. So what proportion should we start with? Any ideas? Well, we want pi over 180, right? Because those two things are equal to each other, and we know that we can convert easily back and forth between them. And if we set that equal to this over here, we want to find 30 degrees, right? So should I put 30 degrees in our proportion? Should I put that in the numerator or the denominator?
Denominator.
Right, because we want our angles to be in the same place in our proportion. Now, if we use algebra, how are we going to multiply this out? Cross
multiply.
That's right. So 30 pi equals 180x. And then what's our next step? Divide by 180, right?
Mhm.
Now we have x equals 30 pi over 180. And if we reduce that 30 over 180, we get 1/6 times pi, or we can write that as pi over 6. And if we go back up to the unit circle, just to double check, we can see that pi over 6 does equal 30 degrees. I'm not sure what I did on my math here. X equals pi over 6. Yeah. Okay. So we can see, based on what we've proven, that x does in fact equal pi over 6. And we started with 30 degrees, right? And if we were to go back up to this triangle, we could write this 30 degrees as pi over 6 as well. It means the same thing. So if we have one last example of converting from radians to degrees, how should I start this one?
Is it pi over 3 and then x over 180? No.
Let's see here. X over 180, and then like this.
Sure.
Well, the problem I have with this is that we don't have our original pi in here. So pi over 180 is how we're always going to start, because we know that's constant and we know that they're equal to each other based on the unit circle right here. And I mean, we could use these as well, but they're not as pretty because they have fractions. But pi over 180 are two things that are equal to each other. So we're going to start with that. And then we're going to bring our pi over 3. And we're going to put that over x because we want to have our degrees in the same spot, right? And we also want to have our radians in the same spot. And looks like we have that. X is our wanted value of degrees because we want to convert 2 degrees according to the problem. And how will we evaluate this equation?
Cross multiply?
Cross multiply, that's correct. So we'll have, according to our cross multiplication, pi x equals 180 times pi over 3. And since we have multiplication and division here, we can just take 180 divided by 3. And that's going to give us 60 pi. And these pi's are going to cancel out again, right? Then we have x equals 60, and that's in degrees. So what we're saying is 60 degrees is equal to pi over 3. And if we go back up to the unit circle, we see that we are correct. Where did 60? Right here. So based on that, we can also substitute that into this triangle if we were to want to. We could also do the same process with the 45-degree angles. And we'll end up getting pi over 4, and the unit circle shows us that as well. And I think that concludes our lesson, and hopefully we can apply that to some problems, have some extra examples, but we're not going to do that. That is the end. Yay.